and I'll discuss some. I'll introduce also the Levy processes and motivation, and then I'll address the usual methodologies that the literature has discussed and doing these simulations, and then I'll introduce my results and give you some pictures that hopefully drive across the message, right? So the main object of study here is that you have a Levy process. In this case, it's a stochastic process used to model risky assets, and we want to simulate as best as we can the final state, the maximum of the process, and the time it achieved this maximum, right? And my only assumption is that I can actually simulate the marginals of this process. So why is this important? Well, if you use the exponential Levy model, say, or if you build more complicated models on top of this one, then usually the stock prices model as S0 and the exponential of this Levy process. This is completely analogous to the exponential Gaussian model or Brownian model, right? Where the exponent here is typically Brownian. Then in this case, if you want to price some options, let's say hindsight options, look back, barrier options, you need access to these variables, right? Which are just functions of these three variables I introduced at the beginning. It's also used under the real world measure to assess risks. So to measure, say, the mean drawdown or its duration or the so-called ulcer index, right? So in a way, this describes how much it can oscillate in a short period of time or on a given period of time, right? Need not be short.
Sorry, what's this ulcer index? So what does this mean?
Ulcer index? Yes, it's a measure of how much it drops from its previous maximum.
Okay. I see.
Yes. So it's sometimes found mostly on economics and sometimes in very applied financial maths, not financial, sorry, areas, not really financial maths. But So, for example, so this is the mean drawdown or absolute drawdown, because it's the actual fall from the price, but now for the stock process, right? So ST bar and minus ST, and here you have somehow this percentage in the drop, and then you square it, take averages, and then square root. That's what the ulcer index is essentially, and this 100 is just to turn it into a percentage. It's just, in a way, it's a measure to assess risk of a price dropping, right? Okay, so these quantities are also related to the prices of other options. Say if you have a perpetual American option, you can recover this price using a formula that relates expectations of this guy right here for an independent exponential time horizon t. You can also use these Levy processes to model Q size. You can use it to simulate the Wiener-Hopf factors if you have some other kind of formula in the fluctuations of the path. Or, as I said before, in more complicated models driven by Levy processes, say, solutions to SDs. In this case, people usually draw increments and do like a skeleton, so like an Euler scheme. And if you know the maximum fluctuations of the driving process, you can get a rough idea of how far off your estimated path is from the actual solution to the SD, right? And now what I want to do, or the problem I want to address, is estimation of this kind of expectation. Okay, where G is some payoff function. We will address some continuous payoffs and also some discontinuous payoffs. All right, now I'll try to go slowly. So first of all, what is a Levy process? Well, this is the technical definition. In principle, it's a stochastic process that is right continuous and has left-hand limits, similar to a distribution function, but it can also jump downwards, upwards. It can have a continuous component like a Brownian motion. And the other condition is that it must have independent and stationary increments, just like Brownian motion. So in a way, or in a strict sense, this is a generalization of a Brownian motion, right? And of course, examples are Campon-Poisson processes and Brownian motion. These Levy processes have a explicit characteristic function, and there's three parameters essentially, which is a drift, a Gaussian component, and the measure jumps. So this measure news roughly measures the average number of jumps you expect on a certain band on the unit time interval. Okay, and all Levy processes can be seen as the limit of Poisson processes as you add more and more jumps. Of course, you can't have infinitely many large jumps, otherwise this would also in a nonsensical way, but you can add more and more smaller jumps so that it jitters. It jumps upwards and downwards, and somehow these jumps, even though they could be infinite and even not summable, they somehow cancel out, just like the fluctuations of a Brownian motion. And, I'll give you an example here. So this is a Poisson process, and I'll increase the number of jumps until I get something that resembles more and more a true Levy process, right? So it's all over the place. It has some kind of jittering similar to Brownian motion, but of course it's discontinuous. Now on top of this, you could add a drift, and you could add a Brownian component. So it could actually have a continuous part, okay? In general, you can decompose it, as I said before, as a drift, a Brownian component, large jumps, so a compound Poisson process, and this limit of compound Poisson processes that have increasingly more smaller jumps. And this beta right here will be a measure of roughly how many small jumps you have. This beta we can call the Blumenthal-Gettur index and can lie anywhere between 0 and 2. This beta will guide or will appear in the convergence speed of all the approximations that we will handle, right? Because as you can see, this jittering behavior will depend heavily on how many small jumps you have, how much oscillations here you have. Yeah. Okay, so going back to the problem, I want to get these three guys. And the basic approach is doing a random walk approximation. So you discretize time into uniform time intervals, and then you do just the increments, right? You do a random walk. If you do this, of course, it's reasonable to expect that the maximum on the random walk, which is this guy right here, will get closer and closer to the actual supremum as you take larger and larger little n here, discretization parameter n. Of course, the time when this maximum is achieved should get closer to tau, and the final value is exact. You don't need to approximate it. If you do this, the question is, okay, so for a given little n, how far off am I from the actual supremum of the path? Right? The actual maximum that the Levy process took, and how far off is the time? In this case, since I'm estimating expectations, I want to know the bias under, say, a continuous function, right? And the answer is that if you look at this difference right here, then the average decay, the decay of the average distance is of order n to the -1/2 if you have a Gaussian component, and otherwise it's n to the -1 over gamma, where gamma is related to this Blumenthal-Gettur index. In particular, it never gets better than n to the -1 or worse than n to the -1/2, right? So it's somewhere in between. It's always decaying polynomially. Okay, this is some technical things that I don't want to discuss right now. There's another more complicated way of doing these simulations. So earlier I mentioned these Wiener-Hopf factors. These Wiener-Hopf factors are essentially describing the supremum of the path. So this guy I wanted to study exactly, but over an exponential time horizon, an independent exponentially distributed time horizon. So that means if I specify the time horizon, I can't get a description of this guy. But if it suddenly I randomize it, I can get a description. Right. So the problem is that I actually want it for a specified time horizon. So what will I do? Well, I will take n exponential random variables with mean t over n. And then as I add all of these, they will have on average length capital T. And hopefully the variance of this random number will get closer and closer to 0. So in a way, what I'm doing is like a random grid, just like this one. But I do get the exact supremum on this random grid. Of course, the endpoint almost surely is never capital T, but it should get closer and closer to capital T. And if it is exactly T, in that case, you would have the actual simulation, right? So in a way, all the error is narrowed down to how far off is this random time close to the actual capital T. this Wiener-Hopf gamma approximation, as I said, is just draws an exact sample of this guy over this variable Gn, which is the sum of some exponentials, which is hopefully close to capital T. So sometimes it can be quite close to capital T, sometimes it can go way beyond, or it can fall short, right? If you use this approximation, then your convergence speed is of roughly of order n to the minus 1/4 if either beta is greater than 1, so you have too much jump activity, small jump activity, or if you have a Gaussian component, and otherwise it's of order n to the minus 1/2. That's it. If you don't have a lot of jump activity. And again, the error here mostly depends on how far off is this Gn from the capital T. Just like before, the error here depended roughly on how far off is the grid from actually nailing down the time when you had the supremum. Okay, so maybe someone could ask, if I can get exact draws from the maximum and the state over these exponential time horizons, why don't I just stop, say, the first time I'm about to go beyond capital T, or the first time I go beyond capital T? Surely these will decrease the distance between the exponential time, the exact simulation of this grid up to this blue circle, and the actual supremum of up to just capital T, instead of going all the way to this Gn or falling too short, right? And the reason why we can't do that in general is because these exponentials are independent, and in this Wiener-Hopf representation, we don't have access to the exponentials. In other words, you can get exactly these three guys over the exponential time horizon, but you cannot get them together with the time horizon. So I know there is an exponential, right? I know there are some exponential times and that they should be close to capital T, but I don't have access to these random variables. I can have access to these three, but not to capital T in a funny way. Therefore, you can't do like stopping time. You can stop when you're as close as you can, in some sense, right? Now, so what will happen if you try to run a Monte Carlo method to estimate a given expectation of the vector that described? This chi, maybe I failed to introduce it, but this chi is the triple consisting of the state, the supremum, and the time. And I want to estimate it using Monte Carlo. So I will take a little n, which is the approximation, let's say depth, and then I will draw capital N independent samples from this guy, evaluate the function g, and take an average. How far off, how big can this error be? Well, this error is roughly, it's an inequality, but it's roughly equal to the bias. So how far is the expectation of this approximation from the expectation that I actually want to estimate, plus the Monte Carlo error. So in drawing n samples, how far off is this mean from the actual expectation? The Monte Carlo error is something you usually can never get rid of, and it's almost always of order epsilon to the minus 2, right? Why? Because it's essentially the variance of this term here. This average here is unbiased in the sense that its expectation is, of course, the same expectation as this guy, but they're independent samples. So the deviations from its mean are essentially the variance, which is the variance, the sum of the variances over n squared, which is just the variance over n, right? So if I want to be accurate, if I want this difference to be smaller than epsilon, then this guy will roughly have to be of order epsilon to the minus 2. Okay, and that's always the case. That's unavoidable. So really, what I want to improve on is on the bias of my approximation. I want this guy to get as close as possible to this expectation right here. And under the methods that I described earlier, this guy always decays polynomially. It always has this kind of decay, and it should be a minus. Sorry, should be a minus in the exponent. And this gamma is always somewhere between 1 and 2. The specifics depend on the model you're actually working with, and if you're using a random walk or the Wiener-Hopf approximation. But anyway, it's always the full complexity of what you need to run in your computer will be of order epsilon to the minus gamma minus 2, right? Epsilon to the minus gamma is what you need to invest in the computer to get something that has a small value, and epsilon to the minus 2 is just from the Monte Carlo error, so from the number of samples that you need to repeatedly draw. Okay. So now I'll go forward and present the new method. So I won't explain exactly how this comes about, but of course, if you have questions at the end, I can explain roughly where this idea comes from. For now, I'll just take it as a fact, okay? I have my vector here of interest, which is just xt, x bar t, and tau t, and I know by a certain theorem that there is a stick breaking process, Ln, this is the construction, I'll get into that in a bit, such that if y is a Levy, there is an independent Levy process of this stick breaking process with the same law as x, such that this equality holds almost surely, right? So now let me get back to what the stick breaking process is. The stick breaking process is called like that because you start with a full stick of length capital T, just a full time horizon, and you draw a uniform random variable, and you break the stick at that length. So this bit you drew is now called L1, and what remains will be further split into a uniform bit, and then you will keep breaking it at uniform lengths, right? Of course, the remainder and the sizes of the sticks that you get each time decreases geometrically fast, right? In fact, this Ln is essentially the product is t times the product of a number of uniform random variables. All right. And now the formula. In this case, this is just the sum of the increments. This is completely natural, I guess. Right? You have a xt, and you will draw increments of your process from time 0 to time time ln, then from ln to ln minus 1, and so on until you get to capital T. So it's reasonable to expect that you will have this coordinate at least. Now for the second coordinate, you will have an error that has the same law as the original guy you wanted to simulate, but over a geometrically small time horizon. And the increments that you sampled, you will only need to take the positive part. That means if you get a positive number, you keep it. If it's negative, you put 0 over here. And over here, you get, as I said, as before, the same law that you want here, but over a geometrically small time horizon. And in the sum, you will get the lengths of the sticks, and you will add them only if the increment you had is positive. So in a way, this guy you can simulate very, very easily. You just need uniform random variables here and increments of the Levy process here and doing some operations. And over here, you have an error that has roughly the same law as the original guy you wanted, but over a geometrically small time horizon. And that's what we will exploit throughout, okay? Now, of course, if I want an approximation, I still can't do this exactly, but I can draw this exactly and do and get something that's quite close to this thing and costs nearly nothing, right? So that's the increment and the positive part. Of course, this is inspired by the structure that the other increments had, right? This positive part here. And then I'll add the final remainder of the stick in my stick breaking process if the final increment was positive or not. Okay, so it's something very simple. This is the algorithm. There's nothing to it. It's not complicated at all. You can all code it if you pick your given Levy process. And now let's explore how fast it converges, right? Of course, intuitively, the error I'm making comes just from the final bit, because this guy is exactly the same, and here I'm doing something slightly different from what I should have, right? And this theorem describes precisely this error. The error has this law, of course. It's exact in the first coordinate. In the second coordinate, it has this kind of error. In the third coordinate, it's just this error right here. In particular, the error over here is bounded in expectation by t times 2 to the minus n. So as I said, it's of course geometrically small. Moreover, the error here will also be geometrically small. I'll get to how small it is or how fast it goes to 0. and it has lighter tails than what you would usually expect. For instance, you could have a Levy process that has infinite expectation, right? So its positive jumps have no mean. They could be like Cauchy distributed, say, and still make these approximation have finite expected error here. Why? If the negative tails are light enough, say they're I don't know, exponentially distributed or nearly exponentially distributed, then this error right here will have light tails. And the reason for that is this simple identity right here. The maximum of the path minus the positive part at the end is exactly either the supremum, so this is the case when this guy is negative, or this difference, right? If this guy is positive, then you get this difference. And it's the smallest of the two because I'm always subtracting the positive guy, right? And moreover, this difference right here has the same law as drawing my process like backwards. And running the process backwards, all positive jumps are suddenly like negative jumps, so there's a distributional property over here. And the moral of the story is that this approximation has often lighter tails than what you would expect. So you can estimate something that has very fat tails and still have an approximation that has very thin tails somehow, right? So this is a nice property. It makes the algorithm also more stable numerically. And now this is the speed of convergence that I wanted to get to. This gamma that of course is a function of this beta will describe the geometric decay of the average error that we make in this approximation. And of course it has a roughly complicated formula, but the moral of the story is that this number right here, this guy to the -1, is anywhere between 1/2 and 2/3. So the slowest it can be is 2/3 to the n, sorry. So it decays quite quickly. And in the best case scenario, it's a 2 to the -n, or 1/2 to the n. Okay. And of course, you can also describe how fast the second moment decays, the third, any number of moments. But for our purposes, I'll just restrict my attention to the first moment and the second moment, because we will need it later. And the second moment always decreases at the rate 2 to the -n. Okay. So going back to how costly this will make my Monte Carlo method be. I'll have my Monte Carlo error here, which is always epsilon to the -2. But now here the bias decreases geometrically fast, right? It's of order eta to the n for some eta, and this eta is anywhere between 1/2 and 2/3. So it can't get arbitrarily bad in some sense. Therefore, the error is of order logarithm of epsilon times epsilon squared. And before, you remember it was epsilon to the minus gamma, epsilon to the -2. And this gamma was anywhere between 1 and 2. So just to make it a bit more concise, I'll put like an analogy, right? Let's suppose that I want to estimate some quantity and I want a precision of 10 to the -3. And I'll assume that each computational step takes like a single byte of memory, right? A memory, because we deal with these quantities all the time when you have I don't know, a song stored on your USB or a file, right? A video game, a picture, whatever. On the random walk approximation, the first process approximation I described, the final cost of the Monte Carlo estimation is anywhere between 10 to the 9 and 10 to the 12, depends on the specifics. So it's anywhere between a gigabyte and a terabyte. For the Wiener-Hopf gamma approximation, it's anywhere between a terabyte and an exabyte. And for the SB8 is just around 10 megabytes. It's less than 10 megabytes, right? So you can already tell that this is a massive improvement, right? These you can store almost everywhere. Gigabytes are already a bit costly, right? And terabytes, yeah, let's not get there. So, and this improvement, of course, gets more dramatic the more precision you want. So the smaller epsilon, the epsilon, the more dramatic the improvement is by using this stick breaking approximation. Okay, now I don't know if the audience is familiarized with multilevel Monte Carlo, but I will introduce it briefly. I will give a bit of an idea of how it comes about. You'll remember that in this approximation, I just fix the final level of approximation, little n, and then I draw n, capital N, independent samples, and I do the average and say this guy should get close to the actual expectation. But some clever men at some point decided to the question of is there a better way of doing this variance part, right? I have usually this guy, and I would like to do something better. I would like to make use of all the approximation levels that go all the way from little one from 1 to little n. Sorry, right? So what I did is I will do an approximation. So without this sum, this looks like a usual Monte Carlo approximation, but for level k. And now I somehow add them up from k equals 1 to n, right? Of course, now I have many more free parameters, and the question is does this actually help at all? Well, the bias of this estimator will be the same as that of chi-n, right? Because these di's are the differences between one approximation and the next level. So you will get here, when you take expectations, the nk cancels with the nk, and you get the sum of this expectation. And then you get a canonical, a telescopic sum, sorry, and you will only get the final term, right? So the expectation of this guy will be just the expectation of the final guy. So it has the same properties as just the Monte Carlo guy. This guy has the same expectation, right? Has the same bias, but we'll get an improvement on the from the variance side. So now instead of having these variance, right, which is just the variance of the final guy I'm approximating divided by n, I will have a slightly more complicated version of the variance, right? Which is you take variance, everything is independent, so it's just the sum of the variances. Then you square this guy. You have the sum of nk time over nk squared variance of di, and it simplifies to this. So now I have parameters to play with. I can play with these nks. You can optimize of these nks. It's not so complicated to do, and at the end you will get the following result. If your bias decreases at a certain geometric rate, and your variance between two levels, so the variance of this guy, decreases at a certain other geometric rate, and the complexity of this simulation is also geometrically growing at a certain other rate, then this is the full multi-level Monte Carlo complexity that you get. So, okay, this is a bit hard to process immediately. So I'll first explain what will happen, say, in the random walk case. Of course, in the random walk case, this doesn't decrease geometrically fast. This doesn't decrease geometrically fast, and the complexity just grows linearly. So what am I supposed to do? Well, you just play with it. So what you'll do is, instead of doing an approximation at level n, so discretize the grid in n steps, you will discretize the grid in 2 to the n steps. So immediately the bias decreases geometrically fast, right? It would be like substituting, let's see, here n will be substituted by 2 to the n. So now you will get something geometrically small. You force it to be geometric. And the variance between one approximation and the next one is also geometric. And the cost is now geometric as well, because you have 2 to the n time steps, right? You somehow play tricks with it so that you can actually embed your approximation model into this scheme. And typically with the random walk approximation, you will be within this scheme. Typically, the variance doesn't beat the cost, and you will be you will have a suboptimal case. Just for comparison, I should have added it to the slides. But what you get, the complexity you get in the normal Monte Carlo is under any of these three cases, you always get epsilon to the -2 minus Q2 over P. So there's essentially no Q1 over here, right? And the multi-level Monte Carlo allows me to reduce the cost by Q1 essentially. Of course, when there's a tie, you can't get something positive, so you only get a logarithm. And if the Q1 actually beats the cost, so the variance beats the cost, then you get just optimality, right? A Monte Carlo error, the same error that you would get just from doing exact Monte Carlo, right? So in other words, sometimes you can balance things out so that it has the same cost as doing an exact Monte Carlo, so with no approximation error. Sometimes these two decay at the same rate, and then you have like a constant here, and you add them up from 1 to n, and this little n will be a logarithm of epsilon. So that's how you get this logarithm squared. And sometimes you just reduce the cost by a little bit, right? And how much is that little bit? It would be the q1 over p. Okay, that's the moral of the story. What will happen under this stick breaking approximation, of course, is that you don't need to play this trick I described earlier with a random walk. You immediately already have a geometric decay of the bias. The variance is also decaying geometrically. This was the second moment I described earlier. This is why we need it. And the cost is simply linear. You just need to draw n sticks, n uniforms, and compute these products to get the stick breaking process all the way to approximation n, and then draw the increment. So this has linear cost. So after you plug this into the MLMC, you always get optimality. You always get an algorithm that has cost epsilon to the -2. Essentially, you got rid of the logarithm I described earlier. Right now, you're in this rate. You only have epsilon to the -2. What you would get if you had an exact simulation. You essentially can't get better than that. And just for completeness, I'll explain what happens if you do this under a random walk approximation or under the more complicated Wiener-Hopf approximation. If you have a variance gamma process, so this now depends on what process you're working with and the specifics of these Blumenthal-Gettur index I described. It will get anywhere close to epsilon to the -2, sometimes optimal. Sometimes it's near optimal, so you only need this additional logarithm squared. Sometimes you get epsilon to the -2 minus delta. And this is all, of course, if you work with Lipschitz functions, right? So if you have a nice call option, a put option, or a mean drawdown, stuff like that. And if you have a barrier option, right? So there's a jump in the payoff, because sometimes you get the payoff, sometimes you don't. So sometimes it's 0, it rounds down, sorry. Then the convergence is much slower, and the quality of this estimator is much worse. In the near optimal case, it stops being near optimal. In the optimal, it also stops being optimal, and here it just gets worse by a factor of epsilon until -1. In the Wiener-Hopf Monte Carlo, the story is nearly the same. You get anywhere between epsilon to the -c or epsilon to the -4 if you use the multilevel Monte Carlo, and otherwise you get between epsilon to the -3 and epsilon to the -4. Okay, and just to compare these methods once again, I will now show you some pictures where I contrast the stick breaking algorithm with just n steps, and the uniform discretization, the Euler scheme with 2 to the n steps, so the one where we had this uniform grid. Okay, and this picture shows how quickly the bias is converging to the bias converging to 0. So the bias would be the difference between this black line and the blue line, or the black line and the red line. The blue line displays how quickly the stick breaking algorithm is converging, and the red one is the one for the random walk approximation. So even if you put the random walk at time step 2 to the n, so you somehow are cheating, then the SBA still beats the random walk approximation, right? They're actually kind of comparable in some sense, but of course the SBA will have a linear cost in n, it will just be n, and the random walk will have a cost of 2 to the n. And this is the payoff I worked with. I think I have it here, right? So this is a look back put, and if you now work with a discontinuous payoff, so now this is a barrier up and out call, right? You have this call option, and if you exceed a certain level, then you get nothing. The convergence, of course, is also comparable, right? The random walk approximation and 2 to the n time step is very similar to the stick breaking approximation at just time step n, with just n sticks. Sorry. You can get confidence intervals non-asymptotically or asymptotically if you assume some further regularity and say that you have like some kind of CLT going on, right? Which is not so hard to actually identify. And that's it. That's it for the presentation. I hope it was not too much to take. Here are some references for people that are interested in this topic. And yeah, that's it.
All right. Okay. Thank you very much, George. Do we have any questions?